Hello, we're at the University of New South Wales and I'm Norman Wildberger. This is a problem on linear algebra from the Math 1131 notes. We're in Chapter 1, Question 19, to show that these 3 points, A, which is the point -1, 2, 1, B, which is the point 4, 6, 3, and C, which is the point -1, 2, -1, are not collinear. So we want to show that. So collinear means that they all lie on a line. Not collinear means, therefore, that they do not lie on a single line. Okay, I'd like to approach this question in a graphical way, just to set up a little bit of three-dimensional graphics for you. This is a very useful thing to be able to do in linear algebra. It's not necessary in order to solve this problem, as we'll see. I'm going to give an algebraic solution in a little while, but I just want you to get a sense of thinking about what does this actually look like geometrically? Where are these points? To not be afraid of actually trying to represent these points accurately in a diagram. All right, so let's draw a picture. Okay, and we're going to use the standard three-dimensional representation. Here is the X, Y, and Z axes of three-dimensional space. And we have to put a scale on things. So let's say 1, 2, 3, -1, -2, and so on. And a scale in the Y direction, say 1, 2, 3, 4, -1, -2, -3. And in the Z direction, 1, 2, 3, -1, -2, -3. Now note that the scales don't actually have to be the same in the X, Y, and Z axes, because we are taking into consideration the fact that we're representing this three-dimensional situation here in the two-dimensional plane. Okay, and the whole nature of linear algebra, in fact, doesn't really depend on scaling. Okay, so we can rescale things, and the situation is really essentially the same as far as vectors go. Okay, so how do we represent a point in such a situation? Okay, so let's have a look at the point A. Where is it in this picture? So it has coordinates -1, 2, 1. So it means we're going to go -1 in the X direction, we're going to go 2 in the Y direction, and we're going to go 1 in the Z direction. How can we represent that? Well, one way of doing it is to think about, to actually draw it using a parallelepiped or a box. So we're going to draw a box. And to draw that box, just think in terms of only drawing lines which are parallel to one of the 3 coordinate axes. Okay, so from this one here, we're going to draw a line that's parallel to the Y, and from here, we're going to draw one that's parallel to the X. So we get a point there, and then we're going to draw some ones which are parallel to the Z through that point there, and then we're going to go over like this, and we go up here, across like this. So hopefully you can see a box there whose vertices are the origin, these 3 sort of coordinate positions on the axes, and then these other vertices of the box. All right. So once we've drawn that box, then we can see where the point -1, 2, 1 is, because it's obtained by going -1 in the X direction, and then 2 in the Y direction, and then 1 in the Z direction. So here it is right here. There is the point A. That's an actual accurate up to the artistic ability of me in this case, but it's reasonably representative of where the point A would be if this was actual two-dimensional representation of three-dimensional space. Okay, and what about the point B? Well, we can do it a little bit more quickly now if we know what we're doing. We're looking at the point B whose coordinates are 4, 6, and 3. So we want to go 4 in this direction, and then we want to go 6 in this direction. So there would be 5 and 6. So So 6 in this direction from the point 4 over here. So that means we've been going over, and I can get a sense of that by drawing a parallel to there. Okay, so that's 4 in the x direction, 6 in the y direction, and then we have to go up 3 in the z direction. Okay, so we could actually do that by drawing I hope that looks like another box, and there would be the point B. And how about C, which is -1, 2, -1. So that would be -1 in that direction, and then 2, and now -1. Well, you can see that that's going to be somewhere over here. So the point C is going to be represented by a point there. So in fact, even without any calculation, just having drawn this picture, I can see that these 3 points A, B, and C are not going to be collinear, because if they were collinear in three-dimensional space, then when we represent three-dimensional space in this two-dimensional way, the images would still be collinear. And you can see that A, B, and C here are not collinear. Their images are not collinear, so they're not going to be collinear in three-dimensional space. Okay, but I don't want you to solve the problem that way. I just want to show you how you can represent points pretty accurately, without too much work, just by drawing appropriate boxes whose sides have the appropriate directions to represent points. All right, so let's solve this problem now algebraically. Okay, how are we going to do that? Well, we're going to look at the differences between the points. Any 2 points determine a vector. So the vector AB, okay, is going to be a three-dimensional vector which goes from A to B. So I'm going to actually be calculating this vector here. Okay. But I can do that just using the coordinates. I know where the coordinates of B are. I know A. So the vector AB is obtained by taking the difference of those coordinates. I take the coordinates of B and I subtract the coordinates of A, and I write things down in terms of a vector. Okay, so generally we like to write our vectors as columns, so I'm going to do that here. So I'm going to go from this row. So 4 minus -1 is 5. 6 minus 2 is 4. And 3 minus 1 is 2. So this is a representation of a vector that goes from A to B. And how about the vector that goes from, say, A to C? Well, we get that in the same way by taking the difference between the point there and the point there. So -1 minus -1 is 0. 2 minus 2 is 0. And -1 minus 1 is -2. So that is the vector from A to C. That's in the picture, that vector there. Now, if these 3 points are collinear, these 2 vectors are multiples of each other. So since these vectors are not multiples, right? So it's clear that no multiple of this one is going to be this one here, because any multiple of this one is going to have zeros in the first 2 components, for example. So these vectors are not multiples, and so the points A, B, and C are not collinear. That's a purely algebraic way of seeing this non-collinearity. Later on in the course, we're going to see that the same problem can be tackled in another way by actually computing a determinant. But that's a little bit later on in the course.